When we deal with electricity, we're usually concerned with three main properties of an electric circuit: current, potential energy, and resistance. Since electricity isn't something we can directly see, we often use an analogy of flowing water to explain how these three properties interact. Imagine for a moment you are standing waist-deep in a slowly moving river. Water is flowing past you, and you can feel it pressing against your body, trying to move you downstream with it. We call that moving water current. Now, why does the water in our river flow? Because there is a source of water above where we are, a lake perhaps, and there is gravity. The water flows from the lake, down the river past us, and continues on until it reaches the ground level. Because the water in the lake is raised above the ground level, it has what we call gravitational potential energy. In allowing the water to flow back to ground, we convert that potential energy into a moving current of water. Now imagine a second lake located twice as high above the ground as our first one. If everything else remained the same, that lake would supply a current twice as strong as the first lake. In quasi-mathematical terms, current is proportional to potential energy. As the potential energy increases, the current increases. Double the potential energy, the distance above the ground, and the current will double. Halve the potential energy, and the current will halve. Now suppose that our riverbed isn't completely smooth. Let's imagine a section of rocks that the river must flow past. This irregular surface resists the smooth flow of water from the lake to the ground. We call this property resistance. Again, in quasi-mathematical terms, current is inversely proportional to resistance. As resistance goes down, a smoother riverbed, current flow goes up. The water moves faster because there are fewer rocks to slow it down. As resistance goes up, current drops. The water moves slower because more rocks impede its flow to the ground. We can combine these two relationships into a single one. Water current is proportional to the potential energy of the lake above, and inversely proportional to the resistance offered by the rocks in the river. Believe it or not, this relationship of three properties in our waterfall analogy is exactly how electricity behaves. Let's imagine the equivalent system in a simple electrical circuit. Our person in the water was really there so we could experience the current flowing past. We need something to let us know that electricity is flowing in our electronic equivalent. Let's use a light-emitting diode, an LED. Next, we had a source of current, the lake up in the mountains. Electrically speaking, that's equivalent to a battery supplying a source of potential energy. We'll add a 5-volt battery and connect its positive terminal to the long leg called the anode of the LED. For resistance, we'll use an electronic component that's actually called a resistor. For things to work properly, LEDs always require resistors in series with them, and the resistor value is matched to the properties of the LED and the battery used. We'll see more of this in a later section when we build our first real circuit. And finally, we complete the circuit with a ground path back to the battery's negative terminal. When we make the connection, electrons from the battery flow through the resistor LED combination and back to the battery, creating a circuit. The LED illuminates, showing us that electrons are flowing in an electric current. Our battery supplies a particular voltage, which is a measure of its electrical potential energy. In this example, we've used a 5-volt battery, and our resistor opposes the flow of current with a resistance measured in ohms. In our example, a 330 ohm resistor is appropriate. Here then is the electrical equivalent of our water equation from before. Current is proportional to electrical potential energy and inversely proportional to resistance. Or substituting typical electrical placeholders, I is equal to E divided by R, where I is the electrical current measured in amps, E is the electrical potential energy measured in volts, and R is resistance measured in ohms. Notice that the final version is an equation, not a proportionality statement. This is possible because the units of amps, volts, and ohms are all defined in such a way to make the calculation return the correct answer every time. This simple equation exactly defines how flowing electrons actually behave in the real world, It was discovered in 1827 by German physicist George Simon Ohm and is known as Ohm's law. As you can see, the waterfall analogy helps us understand the relationship between current, voltage, and resistance in electrical circuits. By the way, looking back at our water analogy, have we fully identified what part of our system is equivalent to the battery? Our lake in the mountains certainly supplies the water needed for current flow, but what happens after all the water in the lake is gone? How does the lake fill again? The answer is, of course, the sun. Sunlight heats the water that reaches the ground level, causing it to evaporate, form clouds, and fall as rain back into the lake. For the system to keep working, an external second form of energy is needed, in this case sunlight. A battery works the same way. Its supply of electrons would be quickly depleted if they weren't being continuously resupplied by another form of energy inside the battery. In this case, it's the chemical reaction inside the battery that keeps the electrons flowing. Before we finish our look at falling water, note one more thing. We called the point where our water had fallen as far as it could the ground level. In electronic circuits, there is an equivalent location where there is no remaining electrical potential energy. We call this location the electrical ground of a circuit. It can be physically located in multiple places in a circuit, but all of them have zero potential energy in relation to the power supply of the circuit. They are all equivalent to the negative terminal of the battery in our example.